Assalamualaikum and hello everyone. We want to present to all of you about chapter 3, which is applications of first order differential equations. Our program code is CDCS 143, while for this course code is MAT300. And we are from JCDCS 1435A. Before we start, let me introduce to you our group members. Me as Nur Alisha binti Zulafian, with another my group members, which are Nur Arisha Dalila binti Zulian, Nur Fitri Alia binti Rasidi, and lastly, Nur Afika Adila binti Muhammad Azrin.
Now I'm going to explain the application of Newton's law of cooling in food temperature. A first-order differential equation that describes how an object temperature changes over time based on the surrounding temperature. This means the temperature of food changes over time depending on the temperature around it. For example, when hot food is left in a cool room, it will slowly cool down. At first, the food cools faster because the temperature difference is big. After some time, the food cools more slowly until its temperature becomes almost the same as the surrounding temperature.
This slide introduces the concept behind Newton's law of cooling or warming. According to this law, the rate at which an object temperature change is proportional to the difference between the object's temperature and the surrounding temperature. In simple terms, a hot object cools faster when placed in a much cooler environment, and the cooling rate gradually slows down as it approaches the ambient temperature. The mathematical model for this behavior is expressed as dt over dt equal to k in bracket t minus ts, where t in bracket t is the temperature of the object at time t, ts represents the temperature of the surrounding, and dt over dt is the rate of change of the temperature. The term t minus ts indicates the difference between the object temperature and its surrounding, and k is a constant of proportionality. The equation is considered together with initial conditions such as t in bracket t0 equal to t0 and t in bracket t1 equal to t1, which specify the object temperature at given moments. To obtain the solution for Newton's law of cooling or warming, the problem may be solved by separating the variable and integrating both sides of the equation. This process leads to a logarithmic expression. First, start with the differential equation, then separate the variable and move all terms involving t to one side and the time variable t to the other side. Next, integrate the both sides and evaluate the integral of 1 over t minus ts dt is the natural logarithm, where c is the constant of integration. Next, remove the logarithm by applying the exponential function to the both sides. Then I will write a new constant as a, since e power of c is just a constant. After rearrange, we obtain the general solution t in bracket t equal to a e power of kt plus ts. This expression represents an exponential approach to the surrounding temperature, which is characteristic of Newton's cooling model. As the temperature difference decreases, the cooling rate slows down, reflecting the object's natural tendency to reach thermal equilibrium with its surrounding.
Hi everyone, today we are diving into a super useful physics concept, which is Newton's law of cooling. We will be using the example of freshly baked cake cooling down to make it easy to understand. And this is our problem statement. Imagine you have been just baked a cake at 180 degrees Celsius. You take it out of the oven and place it in the kitchen where the room temperature is at a constant of 28 degrees Celsius. According to the Newton's law of cooling, the rate at which the cake cools is proportional to the temperature difference between cake and the surrounding air. After 10 minutes, the cake temperature is measured at 120 degrees Celsius. From the problem statement, we can list the important values like initial cake temperature T0 equal to 180 degrees Celsius, room temperature Ts equal to 28 degrees Celsius, temperature after 10 minutes 120 degrees Celsius, and lastly the differential equation for Newton's law of cooling is dt over dt equal to negative k T minus 28. The negative sign value at the K is important because it shows the temperature is decreasing. To solve this equation, we separate variable for differential temperature and differential time, which is integral 1 over T minus 28 dt equal to integral negative K dt. And integrate both sides, so we get ln T minus 28 equal negative K T plus C. Next, exponentiating both sides to remove ln, and we get T minus 28 equal to AE negative KT. So, general solution is T equal to AE negative KT plus 28, where A is a constant. Next, to get the value of A, we need to apply the initial condition at T equal to 0 for time and T equal to 180 degrees Celsius for temperature. So, we get A equal to 152. Now, our equation becomes T equal to 152E negative KT plus 28. Lastly, use the data at T equal to 10 minutes and T equal to 122 degrees Celsius to get the value of K. We substitute the time and the temperature into the equation. Therefore, we get the value of K, which is approximately 0.0501 per minute.
Question number 2. What is the temperature after 20 minutes? For this question, we use the general solution of Newton's law of cooling or warming, which is T in bracket T equal to Ts plus in bracket T0 minus Ts e power of negative KT, where T0 is 180 degrees Celsius, Ts is 28 degrees Celsius, K is 0.0501 and T is 20 minutes. To solve this equation, first, substitute the value into the general equation. Then, calculate the initial temperature difference. Next, evaluate the exponent and we'll get negative 1.002. Then, compute the exponential value e power of negative 1.002. Approximately, we'll get 0.36714. And multiply the exponential value with the temperature difference. And lastly, add the surrounding temperature to get the final temperature. And the answer is 83.80528. After the rounding the practical value, the temperature of the cake at T equal to 20 minutes is approximately 84 degrees Celsius.
Hi, in this part we will determine the time needed for the cake to cool to 60 degrees of Celsius. Firstly, we need to substitute 60 degrees into the temperature equation because we want to know when the cake reaches this temperature. Next, 68 minus 328 will get 32 at left hand side. Then we divided 32 by 152 to isolate the exponential term. After that, we add ln on both sides to eliminate the exponential function. Finally, we solve the equation for T and obtain a value of approximately 31 minutes. This means that it takes about 31 minutes for the cake to cool down to 60 degrees of Celsius.
Next, we will look at the last question. If the cake is placed inside a cooler room with a temperature of 20 degrees Celsius instead of 28 degrees Celsius, what will be its temperature after 15 minutes? As we already know, our original T is 180 and our K is 0.0501. So, now the new room temperature is 20 degrees Celsius. We just substitute T equals to 15 into the equation. T15 equals to 20 plus 180 minus 20 exponential to the power of negative 0.0501 multiplied by 15. And we get 20 plus 160 e to the power of negative 0.7515 and we get the answer 65.47 degrees Celsius. Therefore, the cake will be 65.47 degrees Celsius after 50 minutes in a 20 degrees Celsius room.
In conclusion, Newton's law of cooling perfectly explains why the cake cools quickly at first. Because of the temperature difference with the room and the cake is large, which is 152 degrees Celsius. As time passes, the difference gets smaller, so the cooling rate slows down and eventually the cake temperature approaches room temperature, which is 28 degrees Celsius. This shows how powerful Newton's law is for predicting temperature change in real-life situations, from cooling cake and hot coffee to even forensic science for estimating time of death.